So first of all, on behalf of iLEAPS, I'm really very thankful to Professor Burrows for giving us permission to spend your time during this global interview series. So good morning, good afternoon, and good evening to everyone present here. I'm Saurabh Sonwani, an early career representative of iLEAPS and the convener of this program. With me are co-convener Pallavi Saxena and Samina Shamsuddin, our scientific steering committee member of iLEAPS and iLEAPS IPO respectively. We welcome you all to our 7th episode of Drive with iLEAPS on the Wheel of Science, a global interview series. Today, our guest is Professor John Burrows, Vice President of the International Association of Meteorology and Atmospheric Science, and a lifetime member of International Commission on Atmospheric Chemistry and Global Pollution. He is also affiliated with Institute of Environmental Physics and Institute of Remote Sensing in University of Bremen, Germany. However, before introducing him, I would like to say a few words about iLEAPS. So iLEAPS stand for Integrated Land Ecosystem Atmosphere Process Study. It is a global research project of Future Earth, and it seeks to provide an understanding about how interacting physical, chemical, and biological process transport and transform energy and matter through the land-atmosphere interface. Like other Future Earth Global Research Project, iLEAPS is a network to link iLEAPS scientists to key societal challenges related to health, biodiversity, climate, food and fuel security, and ultimately to the United Nations Sustainable Development Goals. It promotes scientific excellence through developing international science initiatives that are multidisciplinary through bringing together the modeling community with satellite, experimental, and field observational experts, and through enabling communication and networking across the international science community. It facilitates such initiative by acting as a communication hub and coordinator of worldwide scientific research in the field of ecosystem, atmosphere exchange, and the impact of those exchange on the key societal issues. Another very important initiative of iLEAPS is to promotion of leadership in science through capacity building in developing countries as well as through their early career scientist network by hosting workshop, ensuring timely and relevant science to be available through their website and training programs. Recently, we conducted Earth and Environmental Day Series 2021-22 targeting South Asia. We also organized iLEAPS Light Conference 2022, iLEAPS OSFlux Conference 2023. We have successfully conducted Global Colloquium Series 2022-2023. We are also actively convened several sessions in EGU, CIRI from past several years and recently conducted a session in IGEC and SOLAS 2024. As we know that there is several challenges faced by researchers in different fields of science and technology. Thus, a motivation is always required to drive the enthusiasm to carry forward research. The key to motivation is to follow the footstep and journey of renowned and esteemed researchers and academicians that help to set the remarkable goal. So this understanding has been behind the present program to provide researchers, especially early career researcher, an opportunity to imbibe knowledge, inspiration, and zeal to conduct their research in direction that is fruitful to for the welfare of science and society. So with this brief introduction of iLEAPS, now it's time to start our program with our guest, Professor John Burrows, who has a remarkable journey in the field of atmospheric science, atmospheric chemistry, physics, meteorology, and global pollution. Now, here I would like to invite Samina to introduce Professor John Burrows. Now, Samina, it's over to you.
Thank you, Saurabh. Thank you very much. Sorry, good morning. Good afternoon, good evening, everyone. And thank you very much, Professor Burrows, for accepting the interview and, to share your experience with our iLEAPS community. Thanks to Saurabh for organizing this interview series. It has been excellent resource for our early career researchers and very useful. So let me introduce Professor Burrows to the audience. He is a professor in the Institute of Environmental Physics and Remote Sensing, University of Bremen, Germany. Professor Burrows is a fellow of the Natural Environmental Research Council, Center for Ecology and Hydrology, Wallingford in Oxfordshire. He is also the science director and a fellow of NERC, chair of physics of the oceans and atmosphere in Faculty of Physics and Electrical Engineering, University of Bremen. Apart from above, he is also a member of several international and national communities, scientific communities and organizations in science, space, global pollution, and meteorology. He also received several prestigious awards and honors, and the list is so long, so I'm just restricting myself from listing it here. He served for societies and ran international projects, editorships, and several journals. Also supervised several BSc, MSc, and PhD students in his field during his tenure. So it's my pleasure to welcome Professor Burrows to this interview series. And Saurabh, the floor is yours to ask the questions. Thank you for being here.
Thank you, Samina. So now we are formally starting
sorry to
questions.
interrupt, Professor Burrows. Sorry to say, but I am actually on invigilation duty. So there is some person in place of me. So I just little bit managed, and I specially come to say you hello. So
hello. Thanks very much.
Sorry.
No,
Sorry
nice,
for the.
nice to see you again.
Thank you.
Thanks, Pallavi. So here we are formally starting with the questions. We usually start with our question related to the career in your education, career path, and collaboration that you had in the past to have, and that helped you to do the role that you have now. So please introduce yourself to the public.
Okay, first of all, my name is John Burrows, and I'm a professor here in Bremen, as I explained briefly. I'd first of all like to thank the iLEAPS committee here for inviting me to make this presentation. It's a great honor for me. Specifically about my background and what motivated me to move in this direction is an interesting question. I was born near Liverpool in a place called Prescott, and this is really close to the birth of the Industrial Revolution. So we had lots of consequences of the Industrial Revolution right before our very eyes. And I remember going to school and the school bus sometimes being stopped because of bad smogs. Okay, so I remember those sorts of things. And these were, I didn't realize that I would then be working later on such matters, but I had a very good education at my junior school and grammar school, which was in a place called St. Helens, and they had a good focus on science. So I concentrated on math, physics, and chemistry. And then for which I'm very grateful to my teachers there, far too many to name. And then I had the good fortune to go to Trinity College, Cambridge, where I studied natural sciences, which is again a mixture of math, physics, and chemistry. And I had then really good fortune to be invited by Professor Brian Thrush to work in his group on my PhD, which was funded by the Royal Society, a project that he had won from the so-called Gassio Committee. And I worked on studies of atmospheric free radicals, the radical hydroperoxyl HO2 and the radical hydroxyl OH. And we were able in that time to measure many important atmospheric reactions. I was focused on trying to understand stratospheric or reactions of stratospheric importance and their pathways. After that, I did a short postdoc in the Harvard Smithsonian Center, where I continued. And as in Cambridge, I used this laser magnetic resonance spectroscopy. So one of my learning phases where I got help from is in particular from the developers of laser magnetic resonance, the developers of kinetics. So Harry Radford was my leader in Harvard Smithsonian, and he was one of the people who invented that particular technique. So I learned about making measurements, doing techniques, and I was enjoying that very much. And then I worked at the Atomic Energy Authority in Harwell, in close to Oxford, in Oxfordshire, and also I had a collaboration with Professor Richard Wayne at the Physical Chemistry Laboratory, and I enjoyed that time very much. We also were making some really important measurements of both tropospherically important and stratospherically important reactions of free radicals. These free radicals are like the worker bees of the atmosphere. They oxidize and transform emissions into, at the end of the day, water and CO2 primarily. Anyway, so we were enjoying doing these things, but I then got an offer to go and work in a new department run by Professor Paul Crutzen, who's famous because now very famous because he later won the Nobel Prize. He was an extremely good scientist, for me at least. He was like a why not person rather than a why, so he was open to ideas. The people who kind of recruited me were Geert Morgat and David Griffiths. So I worked with them initially on measurements, again, of kinetics and spectroscopy, but then Paul asked me to work in measurements in the field. So I started making tunable diode laser measurement systems for tropospheric species, where we measured oxides of nitrogen and formaldehyde, carbon monoxide, these sorts of things. And at this stage, I had also Dieter Perner as my very nice line manager and friend, and he had invented the differential optical absorption spectroscopy technique. And literally over a cup of coffee, together with Paul and Dieter, I came up with the idea, surely this DOAS technology or system or technique should also work from space. And they basically said, yeah, that's probably right. And that was the beginning of a long journey for me in beginning to make measurements, or trying to win projects to make measurements from space using DOAS. So this is a passive remote sensing technique which enables trace gases to be measured. We also use scattering phenomena to measure surface properties and ocean properties. But basically, the newness was this newness of this technique was the application of differential optical absorption spectroscopy in the UV, visible, near infrared, and shortwave infrared. That was very important, from space. And so with luck, I proposed a project called Skyamachi, and in 1989 that was selected to fly on the European, it was then called Polar Platform, but it later became known as ENVISAT. And at the same time, or shortly thereafter, they accepted our proposal. These proposals are always made with a big team, and people like Paul and Dieter and an international group of people were supporting it. They also selected Skia Mini, which was then selected for a quick build, and in 4 years or 4.5 years it was completed, and then became known as GOME, Global Ozone Monitoring Experiment. So in this period of time, I was working closely with ESA, with engineers, with agencies. There's far too many people to name, and of course my international science colleagues who supported me, and the Max Planck. And then when I moved in the early 90s to Bremen, the University of Bremen, so all of these people, I couldn't have done it without them. and I was very lucky. So I'm very fortunate, and I've worked with some really nice people, and now I'm going into retirement, but I've had a great 50-year career thus far. I'm hoping to continue this. So that's my career roughly, and I think it's a wonderful area to work in, because it's both of fundamental scientific importance, and we're working with fundamentally scientifically challenging problems, but we're also working in an extremely society relevant, an area what's of great relevance for our society and hopefully in the future sustainable development. Thank you.
Thank you so much for sharing your excellent and very lengthy career journey. So, as we know that you have served so many positions and worked with so many organizations. So, as you serve one of the most important position as a Vice President of International Association of Meteorology and Atmospheric Science, so can you please make us understand that what IAMS make it unique from other association working in the same domain like atmospheric science, meteorology, and climate science, and what are the recent advancement and achievement of IAMS under your leadership?
Well, let me just first say, this is a very good question. I personally believe science is an international activity. Science doesn't have national boundaries in this sense. So, on the other hand, national boundaries are very important to have stable countries which then are able to support science. Okay, so having a good science culture in your country is an important thing. But the problems that we're working on do not stop at a particular national border. So I'm interested in local, regional, and national problems. And all of the international associations of different types that I've worked with in my career, in my long career in the meantime, have been associated with trying to, are kind of thinking bodies to try and facilitate international science in the areas of atmospheric science and meteorology. So now we can come to the more specifics. I began by going to meetings and making posters and presentations at the international meetings, which were organized by both the International Association of Meteorology and Atmospheric Science and its commissions. So I'll just explain about what YAMAS is. So YAMAS was created about 100 odd years ago at the end of the First World War to facilitate international science across borders. It's a part of the International Union of Geology and Geophysics, which is part of the International Science, or related to the International Science Council. Okay, and these are bodies which are supported by national governments. The Association of Meteorology and Atmospheric Sciences is one of about 10 or so associations and some projects which report to the IUGG, and our job is to try and facilitate in atmospheric sciences and meteorology research. And we do this through having commissions, and one of the commissions is the International Commission on Atmospheric Chemistry and Global Pollution, ICACGP. And this commission about 30 or 40 years ago set up the IGAC, the International Global Atmospheric Chemistry Project. Now that's now part of what's called Future Earth, which is another organization, but we're one of the ICACGP, and thus YAMAS is one of the supporters of these things. Now these structures, there's maybe lots of names, there's a sort of too many names perhaps and things like this, but what we're all trying to do is to facilitate the research. And in fact, iLEAPS is a spin-off from IGAC, in fact. Okay, originally that was something, but when something gets big enough, people set up a new way forward. So iLEAPS has its specific focus on the surface properties. Okay, And so we feel that's something that we support. So at our meetings, we welcome lots of iLEAPS contributions, and they're usually very good, I have to say. And so what is special about YAMAS? The only thing that's special about it is that it's part of a system which is trying to promote international collaboration in atmospheric and meteorological sciences. So this is our raison d'etre. So we're humble people. We're not, we're not giving out projects like national or international funding bodies. We are trying to stimulate the community and provide the community with an opportunity to discuss, network, and thereby promote and develop our science. Okay. So maybe next question or follow-up question.
Sorry.
Yeah, thank you. There is a bit, the internet was a bit unstable for some moment.
Sorry about
So as we know that you're a lifetime member of International Commission on Atmospheric Chemistry and Global Pollution, and you were also part of, as a commission member of IGAC. So can you please let us know about the career journey of ICSE-GP and IGAC from your eyes?
Well, I had the good fortune, as I mentioned early on in my younger years, to go to be invited or sent to conferences by my bosses, my mentors, and present work, but also listen to work or research work presented by other people working in these areas. So ICACGP has had its own evolution, and this evolution has led it to work in global pollution, particularly beginning in the 1950s. So my journey as part of this was initially going to meetings of ICSE-GP, and then I had the good fortune to be invited onto IGAC. There was a kind of a change of generations, so people who had created IGAC, like Paul Crutzen, amongst others, Dieter Ehalt, these people were standing back to let some younger people come through, and I had the good fortune to first of all go onto the IGAC committee, and then after some time on IGAC, I became a member of ICACGP, and I stayed with ICACGP, later becoming secretary, and then later on president. So I helped organize that, and we developed during the time that I've been involved in it, and subsequently I think a better distribution and diversity among the people being involved in it. For example, when I was first involved in it, there were very few Indian or Asian scientists, so there's been a big increase of the contribution of Asian scientists in these areas during the period of time that I've been involved in it. So basically, I had the good fortune then to be, as a result of my work, to be given the honor of becoming a life member of the International Commission of Atmospheric Chemistry and Global Pollution. This is like an honor, so I'm very proud of this. What it enables me is enables me to participate further in the commission and try and facilitate. So I'm still attending commission meetings as an old timer now in this sense, but trying to help in the evolution. It's really important that we have international collaboration and networking in this area, because the problems that we're working on are a global issue.
Yeah. Thanks for sharing your very excellent journey with ICSE-GP and IGAC. I hope there is so many things to learn, and Further, if we are thinking about, as you have contributed a lot to the science in the different kind of domains, so let us know, please, what is your greatest contribution to science and society till date, that as per your understanding, that you think?
Well, I think let's just take society in general first. I think, well, I'd say being a member of my family is an important aspect of that. I think for society, I've trained a lot of students. I've had the fortune to be an institute leader, and both in the UK and in Germany, I trained people. And it's a pleasure to see these people developing their careers and becoming, many now are very important people, much more important than I am, and that's a wonderful thing to see. So I've enjoyed those aspects of being a professor and working in science. It's a pleasure to stimulate people and bring them on for society. And I think all of the people I've worked on are now worked with. I shouldn't say worked with, collaborated with, are now doing well, and that's great pleasure in all sorts of different areas, but a large fraction are very successful in science. Some of them are using their what they learned in teaching or in agencies, managing, or for working for governments. So I'm delighted by that. On the science side, I'd say what I'm most or best known for are these satellite experiments. So the SkyAmachi experiment, which stands for Scanning, Imaging, Absorption Spectrometer for Atmospheric Cartography. So it's a bit of a mouthful. It's actually a real word. It means doing kind of the impossible task, fighting the sky or shadows. It's a real Greek word. It's also an opera, apparently, which is called SkyAmachi. And so this project, which, as I said, we started at the time that I was invited to work on measurements in Mainz at the Max Planck Institute, led by Paul Crutzen. This project became an instrument mission on the ESA ENVISAT, and we had the spin-off, which was initially called SkyMini, but then was later called GOME, Global Ozone Monitoring Experiments. That's a bit more specific name. That was a fast-track development by ESA and its partners. SkyMachi, in comparison, was 50–60% funded by Germany. It had also the Dutch and Belgian governments as partners. So these instrument missions were part of larger satellite, or they flew on satellite platforms. But the reason why they're important is that this differential optical absorption spectroscopy application, particularly in nadir, enabled us to measure lots of tropospheric species, which importantly, unfortunately, can't measure everything we'd like to measure, but the electronic vibrational rotational spectroscopy and vibrational rotational spectroscopy enables us to have, for molecules like ozone, nitrogen dioxide, carbon monoxide, methane, also formaldehyde, glyoxal, and the oxides of halogens, chlorine monoxide, bromine monoxide, and iodine monoxide. It enables us to measure. In the case of chlorine, it's rather chlorine dioxide is the easier one, but these sorts of species we can see. And at the time we proposed this, there were many people who said, oh, this will not work, it's too difficult. But in fact, it works very well. And there are now follow-on missions. The people who were part of inventing it, we've all been forgotten, and that's very good so, because we now have a new generation of instruments. In Europe, we have the Sentinel-5 precursor, and next year Sentinel-5, and a geostationary version, which we also led the conceptual ideas. And in addition, our concept of CarbonSat measuring CO2 and methane is going to fly on the CO2M, and worldwide there are now a bunch of also philanthropic satellites which are using this approach to measure CO2 and methane. So I would say my contribution has been in the development of methods and making the first measurements, kind of like pathfinding the way forward. And what I'm hoping is that we will eventually have a global observing system, which is actually that we require in order to manage the Earth system and provide the evidence base for the politicians to create the necessary legislation and also monitor and test how well we both understand the Earth system and how well we are able to achieve at the end of the day net zero and sustainability. Thank you.
Yeah. Thank you for sharing your so many achievements and contribution, especially related to global observation, monitoring, and satellite observation. So, serving so many organizations. So, many of your work are kind of path-breaking and learning experience for the so many researcher, especially the early career researcher, to build their career into such very excellent domain. So moving further, and here we are having some of your articles, publications on the basis of the citations, and some of the publication in which we are very curious to understand about, as some of the things you have already explained. So here I am just mentioning the publications, and then after you can just mention the brief about the publications. So here I am just mentioning the name. The number one is the Global Ozone Monitoring Experiment, Mission Concept and First Scientific Result. The second one is the Orbiting Carbon Observatory Mission. And the third one that you have already mentioned so many times, SciMASHI, the Mission Objective and Measurement Mode. So here we would like to get enlightened with this significant this
Okay, so
significant work. Yeah,
how
their
this
contribution.
developed was as follows. So I have to do this in reverse order because in the 1980s, I had the good opportunity from my two main leaders there, Paul Crutzen and Dieter Perner, my main line managers and scientific friends and mentors. They enabled or facilitated that I could develop a concept with my colleagues, both in the Institute, people like Geert Morgaard. So we were doing a lot of within the Institute, we were doing a lot of work on obtaining knowledge of the spectra of atmospheric trace gases, also understanding scattering or a whole bunch of different stuff, and of course modeling. Paul Crutzen was a modeler. So we had a very good basis, and the SciMASHI project was developed to use passive remote sensing. So that means using the solar radiation that's coming to the Earth. And it's a very simple idea. We measure the radiation before it enters the atmosphere, and we then measure after it's been through the atmosphere and reflected back to the satellite. And so what we see is absorption, scattering, and emission features. Okay, and so that enables us to measure a whole bunch of different species, and we can do this in different ways. SciMASHI measured near simultaneously in LIM and nadir, and also made solar occultation, which means during the orbit, which was sun synchronous, it measures in nadir, which means looking downwards, so you're looking through the atmosphere, and it also measures in LIM, which looks at the scattered radiation coming to you from the limb of the atmosphere. And occultation is when you observe sunrise or sunset or moonrise and moonset. And these are ways in which you can probe the atmosphere and look at absorptions both in the total, which is mainly what you do when you're looking in nadir, but limb and occultation enables you to measure measure the vertical profile. So we're interested in trying, ideally, we'd like to have 3D measurements of all important gases everywhere at a resolution of say 10 square meters or something, or even better if it was possible. But so we're on a path towards that. And the first experiments like SkyMatchy and GOM were, and GOM basically was a small version. We originally called it Sky Mini, and it was supposed to have both limb and nadir, but there was only sufficient funding for one of those, and we and I selected nadir. So we looked down, we looked through the atmosphere, but we used the spectral information in GOM from about 230 nanometers out to 780 at a high or moderately high spectral resolution, which enabled us to see both electronic vibrational rotational structures and vibrational rotational structures. And so we then deconvolute that, so to speak, and measure the absorption. And then when we understand the radiative transfer through the atmosphere, we can determine the total concentration or possibly a vertical profile, depending on how you do this. And this is what, so GOM was the first one, then SkyMatchy followed it. It also had then the limb and occultation views. And OCO2 is a slightly different, or OCO, it became OCO2. OCO1, or OCO as it was called, unfortunately failed, the launch failed very sadly, but NASA very nicely paid OCO. So my contribution to the OCO was really having the idea in SkyMatchy that we can measure CO2 and methane, and OCO2 and 3 in the meantime are now NASA instruments led. One of the leaders was David Crisp, for example, and he led that, and we were basically supported with that. And initially we provided, for example, the SkyMatchy CO2 and methane relevant spectral data for them to develop their algorithms. So it was I was there working in complementary fashion, and I'm fortunate to have been a part of that development. But you have to say, David Crisp and the team at JPL were the leaders of that one. And we hope in the future that our carbon sat concept, which is a focus on CO2 and methane, will be a great success. But we're also pleased to see the missions from the Environmental Defence Fund, which is called Methane Sat, and the Carbon Mapper Constellation. These are both philanthropic contributions. That is, they're funded outside of it. So what I'm delighted to say is that we had basically our ideas worked, and now we're measuring much better. Now, for example, you can think about doing resolutions of 30 square meter. We also have a satellite support program which is developing aircraft instruments, and where we also are able to show that you can go to much higher spatial resolution. So so these contributions, these papers that I was associated with were sort of barn-breaking first attempts or first concepts to make global measurements, which I think we need. So it's been a pleasure to be part of that. But it's a big, there are many fathers and mothers of success. So I had fortunate to play a role, and I basically said, tell me why this will not work. Because our calculations, when I was young, I would say our calculations show that it's, it should work. And in fact, it does. We have the it's been a great, the development of computers has of course been tremendous. And now the artificial intelligence revolution is making many more things possible. So from my point of view, we're part of the journey, but I'm looking forward to the new results from your generation. Thank you.
Thank you, Professor Burrows, for sharing these excellent research publication. Even though we have gained so much of the information and so many research ideas from many of your publications. So moving ahead, and we just wanted to know about your current research project. So can you please highlight your current research project that um, can possibly contribute and that can play a very important role to framing some policies, can be very much helpful in science and society?
Well, what I'm currently working on with my team, I have to say now I've stepped back from leading the team, but what we're working on here of great importance is developing these aircraft instruments, passive remote sensing instruments to measure both short-lived climate pollutants and the long-lived trace gases, greenhouse gases, methane, CO2. And what we're trying to do is measure in two ways. These aircraft instruments play a very important role in validating the satellite measurements. Okay, so in order to believe satellite measurements that's inferred from, I mean, essentially in a satellite, what you measure is photons coming back to your satellite, having passed, as I said, through the atmosphere in passive remote sensing coming from the sun originally, or thermal emission from the Earth's surface. So we're interested in measuring these things first of all, and then developing algorithms. So I'm hopeful that we're party to the next so helping the next generation of satellites to provide the information that society needs. And usually you also have discoveries. For example, with GOM and SkyMatch, our teams discovered that there's a bromine oxide plume coming from a bromine explosion. So you see lots of things for the first time. I think we've seen a lot of the things for the first time now, but I think what's interesting now is, in particular, this is particularly important for iLEAPS, is to see that we can top-down measure and check the emissions. For example, landfills, a very simple thing. We've recently are publishing now a paper using aircraft elements which demonstrate that what the satellites have been seeing, for example, over the Madrid landfill, are much higher emissions than the people measuring from the ground. And this is similar elsewhere in coal fields. We've worked in Poland and published work there. So we're trying to basically provide an important part of our work is emissions. However, I have also worked in the stratosphere, and I think one of the long-term objectives is to follow stratospheric ozone through its recovery, so-called recovery, and to check that that in fact it's behaving as we think. And at the moment, since the discovery of the ozone hole and its explanation, which we were involved in making measurements which help to our current understanding, we sort of understand it, but we have to see whether, as we're in a warming world, I'm really interested to see also in the stratosphere what's happening there. But probably the main focus at the moment is on making excellent measurements of emissions in their own right, and also as validation for satellites. Thank you.
Yeah, thank you. And yes, we will surely consider your suggestion in relation to the observing the emissions and all. So that will be really fruitful for the upcoming generation, the ECRs, to work on this aspect. So as we know that you are leading so many organizations, international projects, and working in the area of atmospheric science and global pollution from several decades. So, what is your vision and recommendation to achieve sustainable development goal? to achieve the sustainable future? Because we know that right now United Nations is focusing more toward the sustainability and just to build the global sustainable future. So what is your vision and recommendation in this regard?
So, well, thanks very much. Well, my research has been over the last 50 years has been working in different aspects of trying to understand natural processes and phenomena within the Earth's system, which involves the atmosphere, the Earth's surface, its ocean, and with a focus for me in the atmosphere, so the physical, chemical, and biogeochemical processes. Now, this focus has led me to see actually the massive impact of man on the Earth's atmosphere. And this began during my PhD when we were basically engaged to try and understand what the impact of aircraft emission would be on the stratosphere. I think that in the future, in that respect, one thing that in the near future, which we have to understand is the importance or what happens to the debris from satellites as it comes back into the atmosphere. So some people have shown that aluminium in stratospheric aerosols, a significant fraction of it comes from satellites. So one question is, what is that doing, and will it also result in these aerosols result in some kind of dimming effect? Again, we have to see what will happen on that. Anyway, that's the kind of thing that I'd recommend younger people to maybe work on. My vision with respect to sustainability is controlling and managing the human impact on the Earth system such that we maintain biodiversity and have we stop destroying ecosystems, and we live in better harmony with our planet. So in this context, it's important. I think it's very clear, the recommendations from IPCC over the last or since the early 1990s at the latest. It's clear that we have to get out of fossil fuel combustion and move to cleaner alternative energy. This is very challenging and very difficult, and brings new problems associated with it. Do we have enough lithium? Are we going to, mine the hell out of the world somewhere doing that? But so there's a lot of challenges this. But my view is that we can, and be optimistic that we can get out of this dependency on the production of carbon dioxide from either, or the release of methane, which is a very has a much larger global warming potential. So we have to limit the greenhouse gases, and I believe that that's doable, that we can move to alternative energies. I'm hoping that we will stop the Earth temperature to at least 2 degrees above pre-industrial by taking the necessary measures. Now, in order to take the necessary measures, I believe we need a global observing system which comprises ground segment, space segment, and airborne segments, which provides the knowledge that we need to manage our system. I think there'll be lots of things to understand which are coming up, but I'm optimistic that if we move forward and try and manage our releases, then we will in fact achieve sustainability. It'll be very hard, and there's all sorts of potential social problems associated with this, the migrations of people across the world from poorer places to richer places is pressure on society, which we all know about. But I think we have to, it's in the interest of everybody to obtain a sustainable future. And this must, I think, sustainability must include reducing our dependence on fossil fuel, really bring it down to as low as absolutely possible. So that's my view. And I think that's a great opportunity for scientists, particularly young scientists, to get involved in this and make a solid contribution by working on many, many different aspects of the Earth system. And I'm very happy if people work in the atmosphere and in meteorological area, because this is a very important part of our management system. Thank you.
Yeah, sure. Your recommendation are really great, and I hope it will be very much enlightening for and very much helpful for the research, especially for the early career research, and possibly it will be really helpful for the policy making in the in reference to global sustainable future. So further, we wanted to know your opinion. If we are considering your domain, that is atmospheric science, climate change, and meteorology. So what is your understanding? What kind of subject area that are lagging into this domain that need more focus in future?
Well, I think I've made it quite clear in my talk that we are very much in the pioneer phase still of developing this global observing system, which is fit for purpose and meets the needs of our society. So I think there are a lot of areas where we can improve our technology, make better measurements. So the development of better detection systems, and that starts with the measurement of measurements, or basically the array system with the ability to measure absorption, so to measure light and its changes, or electromagnetic, better said, electromagnetic radiation. I think that there's lots of opportunities to improve the detection of electromagnetic radiation, and also we need to improve so-called active remote sensing. We need to improve our laser systems, which are used in differential LiDAR systems, so or dials, so LiDAR systems, so laser ranging systems, basically, which enable you to also measure, and then you can measure day and night. Same is in the radar world. Okay, those measurements. So we're in a process of making important measurements. We need continuity, looking backwards, so that we can compare measurements to see the changes, for example, in CO2 or methane, or in ozone, or in oxides of nitrogen, as human activity changes. So we need these, and that's a big opportunity. Similarly, on the modeling side, I think it's well, artificial intelligence is being pushed forward now. I was last week at the AGU listening to how artificial intelligence is being used in improving the accuracy and speed of prediction and projection systems using models. So basically, I think that we will benefit in this evolution from, we'll certainly benefit from artificial intelligence, but we have to remember that one issue on artificial intelligence is that it's typically pattern recognition in nature. So if your learning data sets do not include a kind of phenomena that maybe suddenly appears, the example being the ozone hole, the question is, will you be able to see it with artificial intelligence? That's a challenge for artificial intelligence, how it's the generalization problem, how you get away from just being dependent on your learning data set. But I think that's an interesting challenge for people to work on. But there's no doubt that we need also improved computing power, and I'm sure that quantum computing, when it arrives, if it arrives, will also provide a great deal of new possibilities. So all of these things will be needed, in my opinion, to basically monitor or measure, monitor, and explain. We need the understanding of what processes are going on, the physics, photophysics, the photochemistry, the chemical reactions, and the biological reactions. How is the biosphere responding? This is particularly important for iLEAPS. How are these complex processes at the surface responding, or in the ocean, of importance to SOLAS? How are these changing as the Earth is both changing naturally and changing as a result of man's impact? And man's impact is both direct in terms of fossil fuel, it's indirect in that we have lots of biomass burning, which is also creating lots of pollution. So we have to have we have to step our game up, people, to actually do battle with this. So I think in terms of atmospheric sciences has a lot of challenges. We have to do each step correctly, and I'm hopeful that the next generation will be really busy with trying to understand the system and make good projections about how it will change and what the consequences are then for society, either in health or in climate change. Thank you.
Thanks for highlighting this a lagging research area, right from the active remote sensing, improved detection system for oxide of nitrogen, CO2, and more. And yes, artificial intelligence can be very much helpful in prediction and projection in the research domain. And yes, also improve computing system. Yes, iLEAPS is also working into this domain and possibly will be improving ourselves in such kind of a domain. So finally, coming to our most important and most one of the favorite question of mine, that is, what is your ultimate message to your young scientists working in the domain of atmospheric science, global pollution, and environmental health?
Yeah,
What do you want to convey? Yeah,
that's a good question. And I'll go back to when I was a research student in Cambridge. I went to a lecture which was given by a very famous person in Cambridge, one of the Nobel Prize winners there. I won't go into details now, but he was actually working in microbiology areas and of interest to the Medical Research Council. But he basically said his advice in one sentence to young scientists is clean your own test tubes. And you think, huh, what does that mean? What he meant is that when you've cleaned your own test tube, you know that they're really clean or not clean. And so his advice is you need to understand the systems that you're working with, whether they be in the laboratory when you're designing instruments, or whether when you're using data measured by other people, or when you are creating data for use by yourself and other people, or when you're using modeling systems. You don't need to know everything, but you need to have a very good knowledge of what you're working on. And if you concentrate on that, you will be able to judge whether the results that you get are of good quality and what their value is to the system that you're looking at. Okay, and that's really good advice, because for example, when I started off, I started measuring reactions which hadn't been measured before, and people said, "Oh no, that can't be right." But it turned out we weren't perfectly right, but we're a lot closer to the truth than previous measurements which had problems in them. So I think as a scientist, you really have to, as a young scientist, you have to learn the mechanics and also the technologies. You have to understand the technology, learn the mechanics of what you're doing, understand the technologies, and then you'll be You're able to be an independent scientist. Independent scientists aren't prima donnas. Independent scientists are humble people who work well in teams, but they are independent thinkers. Okay, and that's what we need in science. So my advice is to young scientists, do this step by step. You start, you know, the life is a marathon, not a 100-meter race. And so you have to go step by step and learn from your mentors and your educators. Be good citizens, and you will succeed if you persevere. And there's lots of different roles in life for all of us. We certainly need good young scientists working in this area, and I think there are good challenges. And I'm hopeful that the next generation will provide the contributions required to enable us to achieve sustainable development. Thank you.
Thank you so much for these great suggestions.
Looks
I
like
hope it will be really helpful to close the interview. And I'm greatly thankful to you to uh, give your time for this global interview series. And now I officially call Samina for concluding remarks and vote of thanks. Samina, over to you.
Thank you, Saurabh. Thank you, Professor Burrows. That was amazing journey about your career, and it was so exciting. And I'm sure that when we publish this interview, ECRs are going to have a wealth of knowledge from your interview. And thank you so much for sharing your time, sharing your experience, sharing about your career journey, everything. And iLEAPS community is greatly thankful to you. And I also appreciate Gary, our science lead, for joining this interview series. Thank you very much, Gary. Also, thanks to Pallavi, who from her busy schedule of exams and invigilation duties managed to join for a short period. I'm looking forward to working with all of you, and I'm sure that we will get more opportunities to collaborate or work together and meet in conferences and all with you, Professor Burrows. And I have nothing more to say. On behalf of iLEAPS, I wish you all a Merry Christmas and a Happy New Year. So if you have something more to say, we are welcome to.
Well, I would like to thank the iLEAPS community. I send my best regards to Gary, who I used to work with for a while, and at CEH, which is a great organization. I'm very delighted that iLEAPS is now located there with its management team, of which you all belong to. So I have to say, it's been my pleasure to participate. This is a great honor for you to decide to ask me. I think I've had good fun in my research mostly. I basically enjoyed going into work every day. There were lots of problems to be solved, but basically working in science is great fun, and you work with good people. It's challenging, but if I would start again, I think I'd follow the same sort of path. And I recommend young people, you don't have to be brilliant. You just have to be a good, honest scientist, and you make a contribution doing those things. And it's been my pleasure to make some small contributions. But more importantly, at the moment, I'd like to wish everybody a very happy end to the year, a Merry Christmas and a Happy New Year. And let's hope that starting in 2025, we start to move to a more peaceful world, and definitely a more sustainable one. Thank you very much.
Here to you also. Yeah.
Thank you very much.